Hey guys, hope you're all doing good. In this video, we will be modeling and simulating the motion of a planetary gear system. Planetary gears are also called as epicyclic gear trains. You will find these type of gears used in automatic transmissions and also in a mechanical lathe. So the planetary gear consists of 4 parts. So you have the sun gear, which is located in the center. As you can see, the sun gear is going to rotate about its own axis. The second gear is the ring gear, as I've highlighted, and this is going to be the housing for the total assembly. And as you can see, the ring gear is going to rotate about its own axis. Finally, we have the planetary gear. The planetary gear is positioned between the ring gear and the sun gear, and as you can imagine, its rotation axis is going to change. Now, in addition to all these components, you can also have a carrier. A carrier is a component on which all the planetary gears are mounted, and in general you can actually provide an input power or take output power from either the planetary gear, the ring gear, or the sun gear. Now, before modeling this entire system, we need to talk about gears in general. Now, gears are in general identified by the pitch circle diameter and the number of teeth, or the module. If you have any two parameters, either the module or the pitch circle diameter, or the module and the number of teeth, you can actually pick the right gear and the third parameter can be calculated. So let me give an example. Say that you have the module and the pitch circle diameter. Then you can calculate the number of teeth, and here is how it's going to work. Module is nothing but the ratio of pitch circle diameter to the number of teeth. From this relationship, you can actually calculate the number of teeth. That's basically it. Similarly, you have something called as the diameter pitch. The diameter pitch is nothing but the inverse of module. If you are using the metric system, then typically we use a module specification. If it's inch based, then you go for diameter pitch. Now, in order for the two gears to mate correctly and transfer power correctly, the pitch circles of both the gears should be tangent to each other. And in addition to this, the module should be the same for the two gears. Now, we can start by creating our own gears in SolidWorks by sketching and then using extrusion operation. That is unnecessary because SolidWorks provides a library of gears according to different standards, and we can actually use this for our purpose, and that's exactly what we are going to be showing you in this video. Now, in this case, we need a sun gear, a planetary gear, and also a ring gear, and we can just use the design library to basically import the appropriate models. Now remember, the internal gear is basically an internal spur gear, whereas the other gears, the sun and the planetary gears, are just spur gears, right? So let's actually click on design library and click on toolbox. Now click on add in now, and then you're supposed to select the unit systems. These are the most commonly used unit systems. So we are going to be selecting the ANSI inch standard. And once you do that, you can actually see various components, right? Nuts, pins, power transmission components, O-rings, keys, and so on. Let's click on power transmission. So here you can see chain sprockets, gears, and timing belt pulleys. Since we are interested in gears, let's click on gears. And then you can see that there are 7 types of gears: helical gears, internal spur gear, and so on, right? Now, depending on the application that you're trying to model, you can actually choose the right one. So we are interested in the internal spur gear and the regular spur gear, right? So internal spur gear will be used for the outer ring, and spur gears for the planetary gears and the spur gears. Alright, so in the next video, what I'm going to do is I'm going to teach you how you can actually import these individual components from the design library and how to assemble them, and then finally how to do the motion analysis. Alright, thank you, bye.